तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. So in our series of lectures on basic electronics, learning by doing, let us move on to the next. Before we do that, as usual we will go through the basic topics on which we dwelt in the previous lecture. You might recall that we talked about the different types of feedback, negative feedback configurations, and how we can get 4 different types of feedback configurations, and we also discussed 3 of those applications. In the previous lecture we discussed about the current voltage converter, which is also known as current controlled voltage source circuit, and we also briefly discussed about the transfer characteristics of the op amp in order to understand the concept of the virtual earth. You might recall that the input voltages between the 2 input terminals of an operational amplifier cannot be larger than plus or minus about 200 microvolt in a typical case. We also saw applications of the current voltage converter. Then we discussed about the another feedback configuration which led to a voltage to current converter, which is also known as voltage controlled current source, and we saw some of the application circuits of voltage controlled current source. In every case you might remember we also showed a simulation experiment, and then we actually went to the laboratory board and then showed the actual circuits that we discussed with multimeters, dual supply and all that thing. So that we will keep doing at every stage, even in this lecture. Before I do that, I want to recapitulate again the basic concepts of the 4 configurations of the feedback that I already discussed earlier. You can see the figure shows the 4 different configurations. We have already discussed the 3 of them, and the last one is what we are going to discuss today. I show you the other figure corresponding to the transfer characteristic of an op amp. You can imagine when the input voltage goes beyond the maximum voltage, namely about 200 microvolts, you find the output becomes saturation because of the large open loop gain of nearly 10 power 5 in the case of the 741. So this, because the voltage is larger, it cannot be larger than the power supply that I apply, it saturates at 15 volts on plus and minus side, and therefore you are left with only plus or minus nearly 200 microvolts, and or in this case you can see 15 volts I have assumed. 15 volts divided by 10 power 5 is 150 microvolts, so plus or minus 100 microvolt is the difference between the 2 input terminals of an op amp. That you should always remember. Now with reference to the current amplifier or the current shunt configuration, you can see this is the schematic of the feedback configuration. At the output side you sense the current because you are connecting the network in series with the load output RO, output resistance of the amplifier. This is amplifier and this is a feedback network, so they come in series. That means the same current flows through also the resistor which I have in the feedback network, and therefore what I sense here is some voltage proportional to the output current, and then that in the on the input side is given as a voltage in parallel to the input voltage and in opposition, phase opposition. Therefore you can see when I have two parallel resistors coming, if I look at the effective resistance at the input side, it is the parallel resistance values of Ri and Rf. No, this is the input resistance Ri and the Rf, the feedback resistor. So any parallel resistance will have effect of reducing the effective resistance, and therefore the input resistance have now effectively decreased due to the parallel combination, due to the type of feedback that I have given at the input. At the output, because the two resistors come in series, the effective resistance is increased with reference to R naught. So this is what you should understand. The input resistance decreases, the output resistance increases. When the input resistance decreases, the input will have to be current and not voltage, and when the output resistance increases, the output is basically a current, it becomes a current source. So that is why it is called current controlled current source. The input is current which controls the output current, and therefore it is called current controlled current source, ICIS, where the I corresponds to current, current controlled current source. Or in basically this is also called current amplifier, because effectively you will get a larger current corresponding to the input current that you give at the two input terminals. And so the actual circuit with a 741 or similar typical operation amplifier is shown on the screen. You can see the current is sensed, the RL is in series with the feedback network, R2, R1 are the feedback part of the feedback network. So the R1, that is R1 gets the current which is part of the I out. So this voltage will have an influence through this resistor at the input. This is the feedback path that you have here, and this is a current source that I have connected at the input. So we should now find a relationship between the I output, the current output, and the I in, the input current. Already I told you, because of the configuration the input resistance is reduced, because you see along with the input resistance there is another network R2 and R1 coming in parallel. Therefore the effect of parallel resistance is to reduce the input resistance. With reference to output, along with the RO, that RL also is coming, so there is and R1, therefore there is a series resistance coming in series with the output resistance, therefore the output resistance is effectively increased. So that is the effect of the feedback here. And if you look at the closed loop gain, the closed loop gain will have to be AOL multiplied by R1 plus R2 divided by RL plus AOL into R1. But in this you would find the AOL R1, AOL which is a large number multiplied by R1 will be a very large number compared to RL, and therefore I can neglect the effect of RL, and then the AOL will cancel, and what I get will be R2 divided by R1 plus 1. So that is R1 plus R2 by R1, which I rewrite like this, R2 by R1 plus 1. So the gain of the amplifier, in this case the current amplifier, is 1 plus R2 by R1. Similar to the non-inverting amplifier, when we discussed earlier, we also got the amplification factor in a approximation is 1 plus R2 by R1, V output is equal to 1 plus R2 by R1 times V in. Here I output is equal to 1 plus R2 by R1 times I in for this circuit. We also know this input feedback configuration will have effects on input resistance, output resistance, etc. In this case the input resistance with a closed loop feedback will be R2 divided by 1 plus AOL B, where B is actually the beta, the feedback ratio, R2 divided by 1 plus A beta, where A is the open loop gain, here we have designated as AOL. So because the feedback action is given by beta is equal to R1 by R1 plus R2, that is the ratio of the output which is fed at the input, fraction of the output which is fed at the input. and so you would find the effective input resistance is going to be less now. A beta is a large value, so R2 divided by A beta can be very small. So the input resistance, effective input resistance is reduced. Similarly, if you look at the output resistance of the closed loop configuration, it will be multiplied by the factor 1 plus AOL into R1. So R1 is a normal thing that you will get, it is multiplied by this large number, therefore output resistance effectively is increased, and therefore the output acts as if it is a current source. So that is why it is called current controlled current source. It has got a small input impedance and a large output impedance, which is a characteristic of a current amplifier. Now we will take a small example. What is the load current and load power in the figure for one given op amp? If the load resistance is changed to 2 ohms, now it is 1 ohm. If I change it to 2 ohms, what are the load current and the power? Now the input is an AC current 1.5 milliampere RMS, and it is powered by plus or minus 15 volts, and the feedback is actually 1K and 1 ohm. These are the R1 R2 values. So what is the current gain? You can immediately write current gain is equal to R2 divided by R1 plus 1. R2 is 1000 ohms, 1 kilo ohm, divided by R1 is 1 ohm plus 1. This 1000 ohm by 1 ohm is 1000 plus 1, it is almost equal to 1000. So the current gain of this amplifier is 1000, and the input is 1.5 milliampere. So what will be the output current? 1000 times the 1.5 milliampere. So I output is 1000 times 1.5 milliampere RMS, that is equal to 1.5 ampere RMS. So this is a power operational amplifier, it can handle higher currents 1.5 amperes. So that what is the load power? Load power is given by I square R. I square is 1.5 amperes, whole square into RL is 1 ohm, so the total is 2.25 watts. If the problem is, if the load resistance is changed, doubled from 1 ohm to 2 ohm, what will happen? The load current is still 1.5 amperes, because load current is not controlled by 2, it is controlled only by R1 and R2, and they are the same, therefore it is same 1000 times input current, therefore 1.5 amperes will remain as such load current, but the load power 1.5 amperes into 2 square into 2, so therefore it becomes twice. When you double the load resistance, the power also doubles. From 2.25 it has now become 4.5 watts. So this is a very typical simple example of the circuit. We can calculate what is the output current and what is the wattage corresponding output power. Now let me quickly show you a simulation of the circuit. So you have a breadboard here, you have a dual supply here, you have a current source because you want to give a current input, you have a current source here, you can give currents in the order of milliamperes or microamperes by increasing the values, and you have a multimeter here which is already set in milliamperes so that it can measure currents in milliampere. You have the op amp and the resistors. Let me just form the circuit. So the op amp goes over here and the wiring is done. This is a circuit that you have here. So instead of the load resistance, I have put the multimeter. The multimeter forms the load. This R2 is here 10K, R1 is 1K. So the gain is going to be 1 plus R2 by R1, 1 plus 10K divided by 1K. 10K divided by 1K is 10. So 1 plus 10 is 11. Therefore the gain of the amplifier is 11. So you can also see here, this is 10K which is coming from 6 to 2 terminal. There is a feedback loop, right? Pin number 6 is the output, pin number 2 is the input, the inverting input. So you put a negative feedback connecting these two through the resistor 10K, and you have the other resistor here which is the 1K resistor. So this is a 1K, and so the gain will have to be 11. Now I switch on the power supply, dual supply and the multimeter, so I can start giving the voltages. Now let me start from microamperes. So if I increase here, now it is 100 microamperes. As you can see, the current input is 100 microampere, and if you multiply by 100 microampere by 11, it will be 1100 microampere or 1.1 milliampere. So you can see the reading is around 1 milliampere. If I increase to 200, it will be 2.2 milliamperes actually. So as you increase the current, you can see the output current also increases nearly 10 times. It should be actually 11 times. It depends on the actual values of the resistors. If there are some variations because of the tolerance, then this factor cannot be exactly 10, it can be slightly less or more. Perhaps that is the reason why you are getting only 10 times and not 11 times. It depends on the typical actual values of the resistor, which has to be measured using a multimeter. Right. Now let me quickly come down and then let me go to milliamperes. Let us give milliamperes. Now I give 1 milliampere and the output current is, this is 1 milliampere, the output current is 10 milliamperes. So if I now go to 2 milliamperes, it is 20 milliamperes, 3 milliamperes means 30 milliamperes. So you can see the output current is increasing nearly 10 times, which is given by 1 plus R2 by R1 approximately. So this is an example of a current amplifier constructed with the op amp, and the wiring is very simple. You can see this is the ground, this top one, and this is the plus VCC, and this is the minus VCC, the blue line, and so the pin number 4 is connected to the bottom, which is a minus VCC, and the pin number 7 is connected to plus VCC, and you have the input current here and the feedback loop, etc. So the wiring is exactly same as what you have here, and so this is a very current amplifier. Now what we have to do is we have to go and perform this experiment on the experimental table. We will do that. So you can see this is the breadboard on which the circuit has been wired. You have the op amp, you have the feedback loop, you have the two resistors R1, this is 1K and this is 10K, and the power supply lines are exactly similar to the simulation. You have, this is the plus VCC, the green is the ground, and the black is the ground and green is the negative that is connected here in this place. You can see that this is the dual supply. Okay, the 3 line plus, ground and minus are connected here, and this multimeter measures current 2 milliampere range. This is measured in current, and there is one more multimeter at the input which also is connected to 2 milliampere. This measures the current at the input side. So there are 2 multimeters connecting at the input and the output, both measuring currents. You have here a current source, and these are the decades. The dot here, I don't know whether you are able to see the light here, so that is a decimal point. So here it shows 1 0.0, that means 10 microamperes. So 10 microamperes is the current. Right now it is in standby position. I change and apply the current now. Now I apply the current to the circuit. The current applied is 10 microamperes, and that is read by this current meter. It shows 0.010 milliamperes. 0.010 milliampere is nothing but 10 microamperes, as you can see. If you multiply by 10 microampere, if you multiply with divide by 1000, you will get milliamperes. So 0.010 milliampere. So this is 10 microampere basically, and because the gain is 11, 1 plus R2 by R1, R2 is 10K, R1 is 1K, as you can see in the circuit on the top. So 1 plus R2 by R1 is 11. 11 times 10 microampere is 110 microamperes, and if it is in milliamperes, it should read 0.11 milliampere, and you can see it reads 0.11 milliampere. There is a decimal point here. So it is exactly multiplied by 10 times with reference to the input current. Now I am going to change this dial to 20 microamperes. I will change this to 20 microampere, and immediately you can go and see what the input current meter reads. It reads 0.020, which is actually 20 microamperes. Therefore I apply a 20 microampere current. Now I want to see what is the output current. In this multimeter I measure the output current. It shows 0.22, which corresponds to milliampere, which corresponds to 220 milliampere. So 20 multiplied by 11 is 220 microamperes, and that is 0.22 milliamperes. So if I now again increase the current to 30, you can see it is reading 30, and correspondingly at the output you have 0.34 340 microamperes. So 11 times it is multiplied, slightly more than 11 times. I already mentioned to you the small variations that you get is because of the resistances not being exactly what we thought it should be, right. If you actually take the resistors and measure using multimeter and use that in this calculation, you would find they will match with the corresponding readings here. But you can see as I keep increasing the current, the output current also increases every times in a linear fashion multiplied by the factor 11, because this is a current source, right. Okay. Now last time I will do some additional value. For example, I have now put 60 microamperes, as you can see here 0.062. So this is 62 or 63 microamperes, that is what it reads here, multiplied by 11 should be around 66 or so, and you can see in the output is around 69 or 68. So you can see the output current is multiplied by 1 plus R2 by R1, which is the gain factor here. Okay. Right. Now having seen the 4 configurations, you would recall the 4 configurations actually give you 4 different circuits. Each one of the for example, they gave you the following important circuits: voltage amplifier, current to voltage converter, voltage to current converter, and current amplifier. So the 4 different feedback configurations give you 4 different circuits which are almost close to ideal situations. So all that you have to do is just use either 1 or 2 resistors maximum in the feedback configurations, and by which you will be able to get with a simple op amp like the 741 4 different excellent amplifiers. One is a voltage amplifier, there is a trans resistance amplifier, trans conductance amplifier, and current amplifier are the 4 different circuits that you got. Now we will move on to the next set of experiments which are very important with reference to operational amplifier, and that is called operational. Why is the name operational amplifier we have? You might recall at the beginning, at the introduction, I mentioned to you that operational amplifiers are known as operational amplifiers because they can perform different types of mathematical operations. What are the mathematical operations that op amps can perform? I have taken few typical examples on the screen. If you see, you can see what are the different mathematical operations that one can perform. Number 1 is multiplication by a constant. That means what? Y output, y is equal to kx, where k is a multiplication constant. Y and x are related by a multiplication constant. It is something a linear relationship, y is equal to mx plus c type of thing. Y is equal to kx. In terms of the amplifier, the output voltage of an amplifier, when it is multiplied by a constant factor of the input voltage that you apply, this becomes a multiplication by a constant. So immediately you can recognize this is nothing but an ordinary amplifier. Any ordinary voltage amplifier, the output voltage is some constant factor of the input voltage. So the multiplication constant is a very trivial example of the mathematical operation that amplifiers can perform, because almost all amplifiers perform this work. Output is some constant times the input. But apart from this multiplication by a constant, you can also get other circuits. One of the important circuit that you can get is a summing amplifier. Y is equal to k times x1 plus x2 for the case of 2 inputs. With the value of k is equal to 1, you find this becomes y is equal to x1 plus x2, a simple summation. Correspondingly, you can think of an amplifier which will give an output voltage which is some k times V1 plus V2, where V1 and V2 are the 2 input voltages. If I choose the value of k, the gain, to be 1, then it becomes a simple summing amplifier. V output is nothing but sum of the 2 inputs, V1 plus V2. Similarly, you also can have a difference amplifier or a differential amplifier. What is a difference amplifier? Y is equal to some constant times x1 difference x2, or when the k is equal to 1, y is equal to x1 minus x2 or x2 minus x1 as the case may be, depending upon which is higher. So you can also think of an amplifier where the V output voltage is the difference in the two input voltage multiplied by a constant factor. The constant factor, when it is 1, this becomes a simple difference amplifier. V0 is equal to V1 minus V2 or V2 minus V1 as the case may be. The sign will change accordingly depending upon which is larger. So this is an example of a difference amplifier. You also have another operation, mathematical, which is much more complex, which is called integration. You can perform an integration. Y is equal to integral of x dx or x dt, depending upon whether you are differentiating, integrating with reference to time or the space variable. So here you find, if I have a circuit where the output voltage is k times integral of V in dt, V in is the voltage input. So it is an integral of the input voltage which is related to the output voltage by a factor k. Then this circuit performs integration of the input voltage. The output is an integral of the input. Similarly, you can also think of another circuit which will perform differentiation. Y is equal to dx by dt. So V0, in this case output voltage will be k times dV in by dt. What is dV in by dt? Is the differential with reference to time of the input voltage V in. So this is also another circuit. So you can see we have 5 different types of mathematical operations to start with, which we will be discussing here. One is the multiplication by a constant where V output is k times V in. Second one is summing amplifier where V output is equal to proportional to V1 plus V2, the two inputs, sum of the two inputs, and difference amplifier where the V output is proportional to the difference in the two inputs, and you have an integration circuit where the output voltage is integral of the input, time integral, and differentiation circuit where output voltage is differential of the input voltage V in. These are the 5 different circuits. Before we go to that, we will try to look at one of the first circuit, which is actually a multiplication by a constant, which is nothing but a normal amplifier, but there is a difference. We have already seen one amplifier which can be treated as an amplifier which can produce multiplication by a constant factor, that is the non-inverting amplifier, which we have already discussed. V output is equal to 1 plus R2 by R1 times V input, where 1 plus R2 by R1 is our k factor, the gain factor, the multiplication factor. You can choose where R2, R1 and corresponding to value of k that you want, so it becomes a simple multiplication by a constant factor amplifier. But there was no phase change. You can also design a very simple circuit for producing the negative multiplication of a constant, that is called an inverting amplifier. So let us look at an inverting amplifier. Again I have recapitulated here, y is equal to kx or V output is equal to k times V in, and the inverting amplifier will have V output is equal to minus k into V in, where the minus sign comes because of the phase inversion. If I give a sine wave, it will become a cosine wave, it will be inverted by 180 degrees. Non-inverting amplifier also can go as a factor amplifier which will perform multiplication by a constant. I already mentioned to you, V output is equal to k times V in. Because we have discussed this non-inverting amplifier already, let me take the example of the inverting amplifier and show you a very simple circuit which will perform this inversion. In many of the books you would find inverting amplifier will be given as the first circuit, most basic circuit in op amps, because you also have here negative feedback, and the negative feedback stabilizes the performance of the amplifier, you know that. When you have negative feedback, the amplifier performs much more reliably, because the open loop gain can be different, starting from some 20,000 to some 200,000 you can have variation depending upon several other parameters of the amplifier. So then it becomes unpredictable what will be the output voltage, but by giving negative feedback you try to stabilize the amplifier, and therefore the amplifier becomes much more reliable. That is the advantage of introducing negative feedback. Now I have here a very simple circuit which you might recognize as part of the old circuit that we already discussed. Here what is happening here? You find there is a feedback resistor R2 and R1. This is actually minus and this is plus, it is not seen here. So minus and plus, so the feedback is negative because the output is connected to the negative input and therefore it is a negative feedback using two resistors R1 and R2. Now what is the output voltage in terms of the input voltage? The expression is V output is equal to minus R2 by R1 times V input. So the multiplication factor now is given by R2 by R1. If I have R2 10k and R1 1k, I will get 10 as the multiplication factor. K. V output is minus R2 by R1 times V1, where the k factor is basically R2 by R1. So how do I get this R2 by R1 expression? Now you can imagine without this part which is connected at the input, without the R1, you can identify this circuit to be a simple current to voltage converter. If I give a current here, the current cannot pass through the amplifier because of the high input impedance of the amplifier. So the entire current will have to flow only through R2, and therefore output voltage is given by R2 times I in, because this point is a virtual earth. So this voltage will have to be negative with reference to the earth because the current is flowing towards that terminal, it is a negative voltage. So V output is nothing but I in into R2 with a negative sign, minus I in into R2, we know that. But what is I in? I in is now generated using a voltage source and a resistance, because this is a virtual earth. The input current will have to be V by R by Ohm's law, V in divided by R1. So you can see V in divided by R1 here that you see in the expression is nothing but I in multiplied by R2 gives me the output voltage. The negative sign comes because the current is flowing towards that output terminal from the ground, and therefore it is negative. So this expression can be very easily understood from this argument. And now the voltage gain, the closed loop voltage gain of an inverting amplifier is R2 by R1, and it is inverting, that means you know there is a phase inversion between the output and the input. This is very similar to the current controlled voltage source amplifier negative feedback that we have employed. We already discussed that earlier, which is actually a current voltage converter. That is why I have shown here V I in is nothing but V in by R1 and V out is nothing but R2 into I in with a negative sign, therefore you get the factor R2 by R1. This circuit with a feedback resistor can also be analyzed from a known theorem that we already discussed earlier. You might recall the Miller's theorem. The Miller's theorem helps you to split the RF, which is the link between the output and the input, the feedback resistor, into two components exclusively, one at the input and one at the output. You might recall that when I split this RF and put here as a shunt resistance at the input and the output, the shunt resistance at the input will be given by RF divided by 1 plus A, where A is the gain of the amplifier. So the resistance at the input will be divided by 1 plus A, because A is very large, RF by A will be very small. So this comes in parallel to the input resistance, therefore the effect is to reduce the input resistance enormously. At the output side, the Miller's resistance will be A times RF divided by 1 plus AIF. Because A is very large compared to 1, this is almost equal to 1, and therefore it will continue to remain as RF. The entire RF will approximately come in parallel at the output along with the load, and therefore the output resistance is reduced effectively because it is a parallel value. So you can see using Miller's theorem we can split the feedback resistor into two components, one at the input, one at the output. The input component is almost negligible because it is a RF divided by 1 plus A, and the output component is almost RF because A by 1 plus A is almost equal to 1. So this way also we can discuss the circuit, and the output is A times V epsilon, where V epsilon is the small error voltage between the plus and minus terminals, and V output minus I in Rf plus V epsilon is 0 by applying Kirchhoff's law for the circuit here. V output, this is the I in Rf, this is the I in V epsilon, you can say. So this V epsilon is nothing but V output by A, so I substitute in the next line V output by A, and I can rearrange in terms of V output and things like that. So V output by I in will be equal to A times Rf divided by 1 plus A, which when A is very large, this is going to be almost Rf, or V output is equal to I in into Rf, which is what we know. This is a, if it is a basic current voltage converter, output voltage is equal to I in into Rf except for a negative sign here. So V output is equal to I in into Rf is the output in terms of the input. This I in now, because of the virtual earth, we are generating using a voltage source and a series resistance R1, and therefore you get the corresponding V output is equal to R2 divided by R1 times V in with a negative sign. Now we also know the input impedance of the amplifier will be reduced Rf divided by 1 plus A, that is what we saw from the Miller's theorem also. That is the effective resistance which will decide. All the other resistance are larger value, therefore the parallel value will always be very close to the smaller value. Miller's theorem helps us to analyze the circuit easily. Now let me do a simple simulation of the inverting amplifier, and you can again see on the screen the breadboard is coming. You have a dual supply. I switch the dual supply. Before that I will form the circuit. The circuit is simple. You have a 741 op amp, and you have a feedback resistor of 10k, and you have a input resistance of 1k, which is connected to the voltage source. So let me do auto setup, then all the ICs and things like that will go and sit in the proper places. You can see this is a dual supply that is being wired. The top one is the negative supply, then the ground and the V minus are connected at the bottom. So there is a voltage source. The output of the voltage source is connected between the input terminal connected to the resistor, which is connected to pin number 2 of the op amp, and the ground. So the value of that input resistance is 1k, the value of the feedback resistance is 10k, and the value of the resistance which is connected to the ground is also 10k approximately, which will be a parallel value of these two resistors. So the wiring is completed, the multimeter is connected at the output in voltage mode, and now let us switch on the power supply. I switch on the power supply, all the 3 power supply. So now I can give the input voltages. The input voltage I have choice, I can give in millivolts or in volts. Let me give it in millivolts. So I increase it, 10 millivolt is the input multiplied by 1 plus R2 by R1, 100k by 10k, which is again 10. So 1 plus 10 is 11, 11 times 10 millivolt is about 111 millivolts, 110 millivolts, that is 0.1 volts, that is what you see here. So I can apply 20 millivolt, then the reading becomes minus 0.2 volts or 200 millivolts. 30 millivolts means 300 millivolts, 10 times more. 40 millivolts gives me 400 millivolts or 0.4 volts. So you can see if I keep on increasing to larger value, then you will find it can also saturate at some stage, because the output voltage cannot be more than the power supply voltage. So this is the inverting amplifier. You can see also the voltage is negative, there is a negative this thing. Now having seen this, let us move to the demonstration. We will see the demo. So you have the inverting amplifier, you have a 10k at the input along with the voltage source, and you have the feedback between the 2 and 6 terminals of the op amp, a 100k resistor, and at the 3 input it is grounded through a 10k resistor. This is meant to balance it, actually to take care of the differences in the input bias current, about which we will discuss at a later time. So I put a 10k resistor, which is almost the parallel value of 10k and 100k, it is about 9k, so I put the nearest value 10k here. Now this is the output voltmeter. Here this is the op amp, you can see the 7 is connected to the rail voltage, which is connected to plus 15, and the bottom black is the ground and the green is the minus 15 volts, and you have the two resistors, the 10k and the 100k resistors connected in the feedback, and there is a 10k resistor which is coming from the pin number 3. So this is a voltmeter, it is measuring volts, and this is a voltage source which you have seen in the earlier experiment. So I can change the dials and change from millivolts to volts, and that is connected to the input of the amplifier between the terminal 2 of the resistor that I have between this point and the ground. That is what I have connected here. This voltmeter measures in parallel. I have connected the voltmeter in parallel to that voltage source, so that I know whenever I change the voltage I will measure what is the voltage I am applying at the input. At the output I have connected this voltmeter, which is again a multimeter in the voltage range. Now I have got here 100 millivolts. So 100 millivolts. So the gain is 100k divided by 10k, that means 10 times. So I have, it is actually 10 millivolt. 10 millivolt, I will come to a lower range, then it will be better. So I have kept it here in 2 position, that means 20 millivolts I am applying. So the reading here is 0.02, 0.02 volts, this is in volts range. 0.02 means 20 millivolts. If you multiply by 1000 you will get it in millivolts. 0.02, if you multiply 1000 it is 20 millivolts. So I have 20 millivolts multiplied by 10 should be 200 millivolts, and what I get in this power supply is 0.20 volts, that means 200 millivolts. So 20 millivolts, you can see 0.02 is coming as 0.2 multiplied by 10 times. If I put 0.3 here, 30 millivolts, you get 0.3 volts at the output correspondingly. If I make it 40 millivolts, you can see again it becomes 0.04 and the output voltage is 40 millivolts for 400 millivolt or 0.4 volts. Now if I keep on doing it, now what I will do is I will increase it in hundreds. Now I increase to 100, so now it is in 2 position, that means 200 millivolts, that is shown as 0.19 or 0.2, right. So this is 0.2 means 200 millivolts multiplied by 10 should be 2 volts, that is why 1.95 you are getting. Now if I change it to 300 millivolts I get 3 volts nearly. If I change it to 400 millivolt I get nearly 4 volts or 3.89. The difference, as you can see, is because the resistors are not precise. If I take 1% resistors and try the 100k, 10k, etc., you would find very close to the exact number that you think. Now if I keep on doing it, you might ask what will happen if I go to very high values. For example, now I apply 900 millivolt, you can see that 0.87 multiplied by 10 is 8.7. Now what I am going to do, 8 volts I am getting, I will increase this still further to 1 volt at the input. So I have 1 volt here, so you have 0.97 volts here, this is 1 volt correspondingly 0.97 volts. So multiplied by 10 is 9.7 volts, that is what you are getting. Now if I put here 2 volts, what will you get at the output? Obviously you will say 2 into 10 should be 20 volts. Let us see whether we get 20 volts. I have put here 2, it is now 1.95 volts and the output is 11.82 only. Now if I go to 3 volts, here it shows 2.93, nearly 3 volts, but the output still remains at minus 11 volts. Why? We say the op amp is now in saturation, because the input voltage is very large multiplied by the gain factor. If it exceeds the supply voltage, which is in this case plus or minus 12 volts, 11.8 is corresponding to the power supply voltage minus 11.8, and therefore it has come to saturation. So if I come to 2 volts also, it is still 20 volts cannot be shown because it is larger than 12 volts that I have applied to the op amp, so it only shows minus 11.82. If I come to 1 volt, then you see I am below the saturation limit, and therefore 1 multiplied by 10 you get 9.76. Therefore I cannot increase the voltage at the input larger than 1.2 volts, because when I multiply 1.2 volts by 10 I get 12 volts, and 12 volts is a maximum that I get from the power supply. Therefore I cannot get any output voltage larger than the power supply voltage. So that is the idea I wanted to explain to you. So you can also see another very important thing. For example, I am again giving 200 millivolt, 0.2 volts, and the output is 2 volts, nearly 1.94. But what is more important is I am applying the red to the input, the black to the ground. That means I am applying positive 200 millivolts, and multiply by 10 I should get minus 2 volts, and you can see there is a minus sign here. This is actually minus 1.95 volts. So all the time whenever I increase the input voltage, the output voltage is always negative. That shows it is an inverting amplifier. The positive voltage is converted into negative voltage. So these 2 points are to be borne in mind. Having seen the inverting amplifier, now we can also see a small variation of the input inverting amplifier, and the variation of the input inverting amplifier is a very useful circuit, which is useful in many buffer applications. For example, I have shown on the screen 2 circuits. One circuit, you can see the output is completely connected to the input without any resistor. There is no resistor, output is connected to input, and the input voltage is now given to the non-inverting input terminal. So V in, V out, the feedback is 100%. When the feedback is 100%, you will find the gain becomes 1. So A by 1 plus A, beta is 1. So A by 1 plus A is nothing but A by A, which is almost equal to 1, because A is very large. So you have a just gain of 1. But then if there is no gain, why do you talk about this amplifier? We talk about this amplifier because the gain is 1, alright, but then the input impedance has increased by enormous value, the 10 power 5 factor, and the output resistance is decreased by 10 power 5 factor, because I have sacrificed the entire gain in the feedback, and therefore it improves every one of the characteristics by that factor. So if it is a 1 megohm input resistance, it becomes 10 power 5 megohm, which is a very large value, and the output resistance is 75 divided by 10 power 5, which is again a very small value. Therefore it becomes an ideal voltage amplifier with a perfect high resistance at the input, low resistance at the output. So this can be used as a buffer amplifier. So this circuit is very useful as a buffer to isolate an input and an output stage, because this has got high input impedance, it provides isolation between these two. So this is a very useful circuit, unity gain buffer. That is why it is called unity gain buffer. You can also have a small variation of the output of the circuit, where the input is given to the inverting input and the other input is grounded. So here you get output minus V in. In the previous circuit, V output is plus V in. So therefore there is only non-inverting buffer, this is an inverting buffer. The two different circuits are both very useful. They provide you as a buffer. The more important circuit is this unity gain buffer with a non-inverting configuration. This provides perfect isolation. So this is also very useful. It is a variation of the inverting amplifier, that inverting and non-inverting amplifier that you have already seen. What we have done is we have eliminated the resistor and we have given 100% feedback. That is why you have this. Now having seen that, we will go down to the table and we will see the last demonstration of this unity gain buffer, where you would find the output is exactly same as the input, there is no difference, but the amplifier is useful because it provides very large input resistance and very small output resistance. It is used as buffer stage between different stages of amplifier. Here you can see the unity gain buffer. The output is directly connected to the input and the input is given to the non-inverting terminal, and the output voltage is measured at the pin number 6. The circuit is shown here, there is a feedback loop here and the input is connected using this voltage source is connected at the input and this voltmeter reads the voltage input here. So in the similar fashion at the output you have one more voltmeter which measures the output voltage, it is in the volt range DC volts, and you have the breadboard connected to the dual supply, the red, the green and the black. This is plus 12 volts, ground, minus 12 volts. So the 3 wires are connected, very similar to what you saw already, and you can now see the output and the input. Now what I have done is I have given 100 millivolts. This is in 100 millivolt position, so I am giving 100 millivolt which is read by this multimeter as 0.10 volts, which is correct. 100 millivolt is 0.1 volt. So what should be the output? Because there is no R1 R2, there is no, the feedback is complete 100%, therefore the output is also the same as that, right. So it is 0.09 instead of 0.1, it is 0.09 because it is exactly not the same as the input, slightly less. Now if I put it into 2, that means I give 200 millivolts, output is also about 190 something. 300 millivolts, output is also about 0.29. So there is no difference between the input and the output, they are almost equal. The input is 0.39 here, the output also is 0.39 here. So and you can also see the polarity is the same, output is also positive and the input voltage is also positive because it is a non-inverting amplifier. So there is no gain, that is what you should recognize, there is no gain here, but still you gain in terms of other features like the input resistance, output resistance and things like that, and therefore this unity gain buffer is a very useful circuit in number of application for impedance matching and things like that. Now you might be wondering, when I go to for example higher values, now it is 0.49, the output is also exactly 0.49. If I go to 0.6, that is 0.59, the output is also 0.59. But when I come to lower values, for example 0.2 or 0.1 here, you find it is only 0.9, it is not exactly 0.1. Why is it so? That brings us to a very important idea that when I have 0, for example, even though it shows 0, it will still have some small residual voltage which we call offset voltage. Even when the input is 0, there could be very small offset voltage, and that is the reason why at very low voltages you do not get exactly the same value at the output as the input. We will discuss about this offset voltage and other characteristics of the op amp in one of the later lectures. So what we have seen today is basically the current amplifier. We also saw the circuit, I explained about the working of the circuit, and then I also showed you a simulation and an actual demonstration of the circuit with all the input current source and the output current meter and things like that, and we also discussed about the different mathematical operations that can be performed using the operational amplifier, and we took one example of multiplication by a constant, and which can be either a non-inverting amplifier or an inverting amplifier. We also discussed about the inverting amplifier, and we saw the simulation as well as the actual demonstration of the inverting amplifier. Then a variation of the inverting amplifier is the unity gain buffer, where you can have 100% feedback from the output to the input. With that you get very high input resistance and very low output resistance, therefore they can be used for isolation and buffer stages, and therefore that is another circuit. The gain in that case is only unity. Even if it is unity, it has got other characteristics, and therefore it is very useful. So 3 different circuits were discussed, and the third circuits were also demonstrated to you. So we will discuss about the rest of the mathematical operations that can be performed, like the summing amplifier, the difference amplifier, the integration circuit, the differentiation circuit, etc. in the next lecture. Thank you.